Welcome to qnawire.
Hi there. Here, a cylinder is connected to a spring and it's oscillating. So spring has a constant of K and cylinder has a mass of M and radius of R. So first we have to write down the rule of the conservation of energy. Let's do this. So cylinder is moving along the x-axis. Therefore, there is no friction and no slipping in the system. So therefore, total mechanical energy is constant. So total mechanical energy is the sum of potential and kinetic energies, and it's a constant value. Potential energy equals to the energy of the deformed spring, or kx squared over 2, and the kinetic energy is the sum of rotational energy of the cylinder and translational energy of the cylinder. The translational energy of the cylinder equals to the mass of cylinder multiplied by its horizontal velocity squared divided by 2. The rotational energy of the cylinder equals to the moment of inertia of the cylinder divided by angular frequency squared divided by 2. So the first term, momentum of inertia of a cylinder when cylinder rotates along its principal axis. So basically for this case scenario, in this case, momentum of inertia equals to mass of the cylinder multiplied by r squared divided by 2. So therefore, the rotational energy of the cylinder equals to mr squared over 2 multiplied by omega squared over 2. So omega in turn equals to v over r, or velocity over radius. So it means that this guy becomes, mv squared over 4. Okay, now let's go back to the first equation. So the left part changes to kx squared over 2 plus mv squared over 4 plus mv squared over 2, and it's all equals to some constant value. So let's simplify this expression. And now we are going to, basically this is a rule of conservation of flow. And now we are going to take the derivative. So let's take the derivative with respect to time. So the first term becomes k over 2 multiplied by dx squared by dt plus 3/4 mass multiplied by dv squared dt, and it equals to 0 because the derivative of constant is 0. So here we have to use a chain rule to calculate each derivative. So it means that the first term becomes k over 2 multiplied by 2x multiplied by dx dt plus second term becomes 3/4 mass multiplied by 2v multiplied by dv dt, and it all equals to 0, right? So we can simplify the expression. So, and here we have to do the following modification. dx dt equals to the velocity, and dv dt equals to d squared x by dt squared, because velocity equals to dx dt. Yeah, as I said already. So therefore, the first term becomes kx v plus 3 over 2 mass multiplied by v multiplied by d squared x dt squared. It equals to 0. So we can get rid of the velocities to solve this equation. So it becomes 3 over 2 mass multiplied by d squared x dt squared plus kx equals to 0. So now let's further simplify the expressions. Unfortunately, I'm not able to compare it to the equation 13 point something as asked in the task because there is no equation attached, but I presume we should simplify the equation to something like this. So it becomes 2k over 3m multiplied by x equals to 0. So this is the equation which describes the motion of the system. And here, and if we just draw an analogy with simple oscillation of a weight on a spring, which looks like d squared x dt squared plus omega squared x equals to 0, where omega, let's label it as, okay, let's leave it as omega, it's equals to square root of k over m, right? So it means that in this case, omega equals to square root of 2/3 k over m. Yeah, I presume that this is a correct solution of this question. I thank you very much for submitting it. I hope I helped you. Thank you. Bye.